Hello class, welcome to exercise 4D, bearings. Today we're going to learn how to use the method that is very common with shipping, and we'll learn how to apply trigonometry to it. In this lesson, your examples and pre-learning will be example 7, stating a direction. And your pre-learning for this will be questions 1 and 2 in the new book and questions 2 and 4 in the old book. And then with one more example, example 8, using bearings with trigonometry. And your pre-learning for this will be questions 5 and 6 in the new book and questions 7 and 8 in the old book. So let's just move straight into the introduction. Bearings are just a way to describe the difference in position. So far this year, we've already used Cartesian coordinates. For example, if I was to draw two axes and mark in the points 3, 2 and 7, 5 and draw a line between them, then with linear relations, we would say that moving from one point to the other, we move 4 in the direction of x and 3 in the direction of y. We also learnt how to describe the line that passes through both points. We can even tell the distance between these points. So that's the way that linear relations would describe it all, but bearings can describe the difference between these points just by stating the direction from the starting point and then the distance that needs to be travelled to the destination. And the directions we're talking about relate to the compass. So let's just draw a compass with north, east, west and south, which you might not know is where the word news comes from. We've also got these other directions: northeast, southeast, southwest and northwest. What bearings does is it turns all of these directions into angles. North is 0 degrees and 360 degrees. But with bearings, we always use 3 digits, so we could write these as 000 direction T and 360 degrees T. T is just a notation for bearings. It's got something to do with true north. I actually probably need to look that up, Anyhow, that also means that east would be 090, south is 180, and west is 270. But the whole point of this is not just to focus on those points of the compass. It's because we often travel in directions that are different. For example, we might travel at 75 degrees true north. I'm going to go into a little bit more detail in the correct section, but just note that we look at 260 degrees as 360 minus 95. So that makes this direction here 260. But as I said, we'll go more into the different directions in the right section. Another point to consider is that when we're working with bearings, they describe the travel from one point to another. So let's draw point A and B. And if I draw a little compass for A, the journey from A to B, we describe as B is bearing theta from A for a distance of x. But when we travel from B, B gets its own directions. So let me draw a little compass for B. So now we're going to describe the journey from A to B as A is bearing gamma degrees from B. And gamma will be this angle here. So you can see that's a different angle. But what you do know is they'll both be traveling x units. It is essential that you do understand this and that you remember that the return journey will have a different bearing. So as I stated earlier, bearings are very important for navigating at sea, as well as any other area where we don't really have roads. In the last section of this lesson, you'll see why it's part of this unit, because we're going to be using some trigonometry to discover distances between points. But before we get up to those lofty heights, I suggest that you pause the video now and do building understanding questions if you're in the new book, and they translate to questions 1 and 2 in the old book. Alright, and I'll see you in the next section. Okay, so when we look at a compass, if we consider north as the start and the end of our rotations, in other words, the start is 000T and the end is 360T, then every other direction we could take is how many degrees we've rotated in a clockwise direction. So what this means is when we're considering our turn or our rotation, we add degrees when we're moving clockwise and we subtract degrees when we're moving counterclockwise. But this will make a lot more sense if we just jump straight into example 7, for which I'm going to have to draw a compass and then draw the points A, B, C and D. And I'm going to call the point at the center of the compass the origin, or O. And now let's draw a line from O to all the points. And this segment from O to A has an angle of 35 degrees with the east axis. And O to B has an angle of 45 degrees with the east axis. And O to C has 30 degrees with the west axis. And O to D 70 with the west axis. Now part A of this example wants us to find the bearing of each point from O. So this is where you really need to take note of what's clockwise and what's counterclockwise. We can also look at breaking it up as two turns, like turning from an axis and then back to the segment, okay? So O to A has a turn of 90 degrees to the east axis, but then we have to rotate counterclockwise back 35 degrees. So our 90 degrees is clockwise and our 35 is counterclockwise. So that means we end up with 90 minus 35 degrees, which is 55 degrees. So we can say that A is bearing 0.55 degrees from O. Now if we consider the point B, or the journey O to B, first we turn 90 degrees to the east axis, but then we have to continue turning another 45 degrees clockwise. So we add clockwise rotation, so we end up with 90 plus 45 is 135 degrees. So B is bearing 135 from O. Alright, let's move on to the next two. O to C, we're going to move 270 degrees to west, and then we're going to move back counterclockwise 30 degrees. So 270 minus 30 equals 240 degrees. So C is bearing 240 degrees from O. And last but not least, we have O to D is 270 degrees to west, and then another 70 degrees clockwise. So we have 270 plus 70 equals 340. And D is bearing 340 degrees from O. Alright, so that's it for A. Hopefully that was really straightforward. You shouldn't get too confused with the clockwise, counterclockwise. And also take note that it's multiples of 90 degrees to each of the main axes. Okay, that's not news, but NESWAT will do. Alright, let's move on to part B, where we're going to have to move in the opposite direction this time. And by that, what I mean is we're going to find what is O bearing from A and D. So let's start off drawing the points OA and D as we understand their positioning from part A. Now I made the compass look a little bit smaller compared to the spreading of the points, and you'll see why in a second, but first let's remember that A is bearing 050 degrees from O. So that meant we had 35 degrees here. And D was bearing 340 degrees from O, and we represented that with this 70 degree angle here. But this time we're going from A to O and D to O, so they're going to need their own compasses. Now some students might find this difficult, but because each one of you is a superstar, as was shown in the geometric reasoning block, you can notice the alternate angles here, right? So north is always north, and west is always west. So those up and down and those left and right axes will be parallel to each other. So that means that where we see 35 degrees here, we must have 35 degrees here. And where we see 70 degrees here, we must have 70 degrees over here. And I better note for the future, in case anyone reads this, we've just used alternate angles. Alright, so let's focus in on the angles I've written on those compasses, and we can now figure out A to O. Now if A is facing north, we're going to rotate 270 degrees west, but then counterclockwise rotate back 35 degrees. So because it's counterclockwise, we end up with 270 minus 35, which equals 235. So O is bearing 235 degrees from A. And looking at D to O, we can see there's that 70 degree turn there. But first we have to turn to E. So we turn 90 degrees to get to E, and then another 70 degrees clockwise. So clockwise is adding, and 90 plus 70 is 160. So O is bearing 160 degrees from D. Right, so you can see those directions are different, and it's obvious that we're moving in the opposite direction. So you really need to think about how each point has its own compass. You might also notice that because the bearing is a return journey, it involves the opposite directions. i.e. north turns to south and east turns to west. Once you've figured out what the degrees are for that, then you need to add and subtract the same alternate angle. Anyhow, I have complete faith in you, so why don't you just pause the video now and work on questions 1 and 2 in the new book, or questions 2 and 4 in the old book. And when you've done that, you can come back for the new section where this now brings trigonometry into the game. When using bearings, we have many opportunities to use trigonometry. The most common way that we'll do it in this lesson is to compare how much we've travelled in respect to a major direction with our actual journey. And by major, I mean north, east, west or south. So for example, let me just draw a compass and map out a journey of 10 kilometres, bearing 0, 4, 0. I could mark in the 40 degrees in relation to the bearing, or I could also mark in the 50 degrees, which is actually more relevant to the east direction. And we could use either one of those angles to discover how far north or east she's travelled. So for example, if I use that 50 degree angle, so we could create a triangle with these 50 degrees and say that she's travelled X distance in the east direction. Now using this triangle, I could also guess how far she's travelled in the north direction, which I'll call Y, because cos of 50 times 10 is going to equal X, or sine of 50 times 10 is going to equal Y. Hopefully you recognise I've just skipped the step where we write it out as a ratio, and I've just put the hypotenuse on the left hand side of those equations. So this is exactly how you apply trigonometry in bearings. I think you might want to pause the video now and think, how could you use the 40 degrees in this situation? And when you come back, we'll get stuck into example 8. Perhaps you didn't go anywhere. Anyhow, example 8 is all about a ship that travels due south for 5 kilometres. So let's draw that starting point with a compass and then mark in the journey. Then it travels another 11 kilometres, bearing 1, 2, 0. So I better mark in a point where the last journey's finished and draw a compass with that as well. I'm just going to mark in the journey so we don't lose it. Okay, so bearing 120 from there is 90 degrees plus 30. Okay, and that's the easiest way to make up something like 120 is to use the 90 degrees of each axis. So let's mark in its 11 kilometre journey. Hopefully that looks like 11 kilometres. Alright, so let's move on to part A where the questions start. And part A is saying, how far east has the ship travelled from the start? Now we can ignore the first leg because it just travels north and south, okay? So we're only going to look at the second leg and we'll just do what I did at the start of this section. So as we move along this journey, you can see that the amount that's travelled to the east is something like here. And from a previous diagram, we know this angle here is 30 degrees. So to find x with this angle, my x is adjacent to the angle, and the 11 kilometers is the hypotenuse. So we're definitely using cos. So cos of 30 is going to equal x divided by 11, or 11 times cos of 30 is going to equal x. And that's a calculator problem. So I'm going to round that off to 9.5262. So that's 9.526. And why 3 decimal places? Well, it's a kilometre, so 3 decimal places are metres, right? So I like that. Anyhow, let's not forget we have a worded question, so we got to give it a worded answer. So the question asks us how far east, so all we have to do is say the ship has travelled 9 kilometres and 526 metres east from its starting position. Okay, so that's it. Let's move on to part B, where we're asked how far in total has the ship travelled south. So this time we do have to count the first leg, because obviously that was all south travel. Then of course there was that other 11 metre leg, and we're trying to figure out exactly how far we've travelled south. So I forgot to mark in the 11 there too, didn't I? So I'm going to draw in right angles to these lines here, and not just any old right angle. I'm trying to make sure one of them is south. I'm going to call this distance here x, and clearly y is going to equal 5 plus x. And don't forget y is our total distance south. Now I should draw in the 30 degrees here, and x is going to equal sine of 30 degrees times 11. So y sine, well, x is opposite to the angle, and 11's a hypotenuse. And when you know the value of the hypotenuse, you should know by now that we just immediately multiply that across. I also happen to know that sine of 30 is a half. So these are one of the few times you don't have to use a calculator. So x is going to equal 11 times a half, which is 5.5. And that means y is 10.5. Okay, once again, worded question, worded answer. Okay, so that's the trigonometry part. It definitely does get a little bit more complicated in the examples or in your questions. But first you better pause the video and have a go at your pre-learning for this, which is questions 5 and 6 in the new book and questions 7 and 8 in the old book. And we'll come back and summarize this lesson. This topic hopefully is going to help you understand two really important topics in the future. The first of these topics is about applying trig to 360 degrees, and this relates to the unit circle. Unit circles are a really important topic, and a lot of students do find that challenging. That's coming up in the second half of this year and will be a big part of methods 1-2 as well. And for those of you who go on and do specialists next year, this whole topic will relate to vectors. Alright, so a successful student from this lesson will understand how true bearings are measured and written, be able to state a true bearing and its opposite direction from a diagram, and finally be able to apply bearings in worded problems using a diagram and trigonometry. Alright, good luck with that. We'll see you back in the next lesson where we'll be taking trigonometry in third dimension. Okay, bye.